Okay, so now we're going to look at how internal energy changes under different conditions. And, basically we'll be looking at some mathematical equations that are involved. Now, remember we said that according to the first law of thermodynamics, delta U, the change in internal energy, is equal to the heat change or the heat absorbed plus the work done on the system. So that's given by this equation right here. Now, let's say we have a process occurring where the volume remains constant. Now, if that is so, based on this equation that we dealt with before, if the volume remains constant, that means that delta V is zero. And if delta V is zero, that means that the work done on the system would be equal to zero as well. So therefore, basically, since W is equal to zero here, that means that delta U will be equal to Q, which is equal to QV. QV basically means the heat change under constant volume conditions. So how do we interpret this outcome? Well, basically what this is saying is that if you have a process where there's no change in volume, there's no expansion against the surroundings or no contraction, then basically all the internal energy change in the system will be due to the heat that is absorbed or given off by the system. All right. So that's basically the conclusion that we can come to based on the internal energy change under constant volume conditions, right? Basically, the internal energy change will be equal to the heat change of the system. Now, what about situations where instead of the volume being constant, the pressure is constant? Well, if the pressure is constant, that means that, well, delta U, which is a change in internal energy, would be equal to the heat change, QP, under constant pressure conditions, plus W. W will be replaced by minus P delta V, which we met before. So therefore, the new equation will be delta U is equal to QP minus P delta V, or we can rearrange it to get an expression for QP being equal to delta U plus P times delta V, right? Now, unlike the constant volume situation that we saw in the previous slide, the change in internal energy under constant pressure is a more realistic situation that is most likely to happen for most processes, right? So basically what this means is that whenever there's a heat change that is occurring in a system, let's say, for example, it's an exothermic process, that means that QP would be negative. Well, that change would be in part due to the change in internal energy and also in part due to expansion against the surroundings by the system, right? Now, most of the thermal energy that would be released in this process will be released as heat, right? But some work will be done to expand against the system. Expansion by the system against the surroundings, all right? So that's basically what we can gain from that equation. And just to give an example, in this slide, we have a reaction here of magnesium plus hydrochloric acid to give magnesium chloride and hydrogen. And hydrogen is a gas which, as we all know, like any other gas, will expand against the surroundings, right? So what we're talking about here would apply to a system such as this. Now, this brings us to a new term, which is called enthalpy, right? And the actual definition of enthalpy is given right here. It is symbolized by the letter H, is equal to U plus PV, right? So basically, the QP that we were talking about before, the heat change under constant pressure conditions, that is actually the same thing as enthalpy. QP is equal to delta U plus P times delta V. And more specifically, QP would be the change in enthalpy, all right? So whenever we're talking about enthalpy changes for a reaction, we're talking about reactions where the heat change is measured under constant pressure conditions, all right? And as I said before, that's what happens in this particular example. The hydrogen that is produced is basically pushing back against the atmosphere, and therefore the system is doing work against the surroundings, all right? Now, as stated here, for most reactions that occur under constant pressure, the heat equals to the enthalpy change. That is true for pretty much the vast majority of reactions. Okay, so what are the properties of enthalpy? Well, firstly, enthalpy is an extensive property, which means that it is dependent on the amount of substances involved. And that will become important for us to recognize when it comes to certain problem solving, all right, exercises. So therefore, if you double the amount of reactants, then the amount of enthalpy change occurring will be doubled as well. Now, because U, P, and V are all state functions, then enthalpy also must be a state function as well. And enthalpy changes have unique values depending on the reaction. So therefore, experiments would have to be done to measure these values. And there are actually tables that have been put together to give you the enthalpy values of different substances. We're going to talk about that later when it comes to enthalpy of formation of compounds, all right? Okay, so just to show you in a more pictorial sense what happens in a chemical reaction, when it comes to, well, let me say this firstly. When it comes to the actual definition of change of enthalpy, it is simply, as seen up here, it is simply the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants, all right? Now, what that means basically is that if you could somehow measure the sum of the enthalpy of the products and the reactants and put them into this equation, then that will give you delta H. Now, this is a very simplified representation of how we would calculate delta H using these values. It's a bit more complicated, but simply put, it's the sum of enthalpy of products minus the sum of enthalpy of reactants. And we can measure these experimentally, right? The delta H values. Now, if the delta H value is negative, that means that the reaction is exothermic, which means that the enthalpy, total enthalpy of the products would be less than the total enthalpy of the reactants, right? So basically, as you go from reactants to products, energy is lost, and therefore delta H is negative. On the other hand, if delta H is positive, we're talking about here an endothermic reaction, in which case the enthalpy of the products would be greater than the enthalpy of the reactants. So therefore, as the reaction progresses, energy would increase, and therefore delta H would be positive. Okay, so another property of delta H is that if you have a reaction, let's say hypothetically going from from A to B, and let's say delta H is positive, then going from B to A would mean delta H is negative, right? The magnitude, in fact, would be the same, but the sign would be reversed. And here's an actual example, the reaction between mercury and oxygen to form mercury 2 oxide. Let me do it over here. So going from the reactants to the products, right? In this case, delta H would be equal to minus 90.83. If you were to do the reverse reaction, then delta H would be equal to positive 90.83. So basically, it's the same magnitude but different signs if you reverse the reaction. That also will become important when we do calculations involving delta H. In fact, here's an example right now. So in this example, they gave you this equation and they gave you the delta H value for that reaction, right? And the question is asking for delta H for this given equation. Now, in order for us to answer this question, we have to compare this equation to this equation, and you'll notice two things. One thing you'll notice is that the products of one reaction, of this reaction here, would be the reactant of the reaction for which you're asked to find delta H. And the converse is true. The reactant of this equation here would be the products, right? So that's the first thing you'll notice. The second thing you'll notice is that all the coefficients for the first equation here, for all the different substances involved, are halved, all right? So how does that help us to determine delta H for this reaction? Well, firstly, if you switch this equation around, if you basically put the products over on the reactant side and the reactants on the product side, that means that the sign of delta H would change from positive to negative. So it will change from plus 52.96 to negative 52.96, all right? And then now, to get from that equation to this equation for which we're trying to find delta H, since all the coefficients here are halved to get this, that means that we'd have to halve the value of delta H here to get the delta H value for the equation for which the question is asking for. So that means you divide minus 52.96 by 2, and that will give you 26.48 kilojoules. And that's basically how that is done. All right? So that's a relatively simple example. Now, let's look at the next example below. In this example, they gave you some information about liquid octane. It says that it is combusted completely to produce gaseous carbon dioxide and liquid water, and at a constant pressure gives off 47.9 kilojoules of heat per gram of octane. So the question is asking for you to write down a chemical equation to represent this information. Admittedly, the actual final question here is not very clear. So let me just explain what it's asking for. What it's asking for is not just an equation like this that we have here, but it's also asking for the corresponding delta H value. And the key thing you need to recognize is that the delta H value here is given based on the coefficients representing the actual moles of the substances involved in the reaction. So in other words, going back to this example right here, the fact that delta H is equal to plus 52.96 kilojoules is based on 1 mole of hydrogen reacting with 1 mole of iodine to form 2 moles of hydrogen iodide. So basically we need to figure out the amount of heat change that will occur for the coefficients given in the combustion, for the different substances given in the combustion of liquid octane, which basically means we need to figure out the balance equation for this reaction. So let me get out of that for a minute, go to my writing software here, and let me delete this and choose, no, which one should I choose? No, let me not use that. Okay, let me use that. Okay, so the equation is C8H18 liquid plus O2, which is a gas, to form CO2 gas plus H2O liquid. So of course, we need to balance this, and this is something that we all should be familiar with. So basically, to balance this, we need an 8 here, and we need a 9 here. Okay, so that means that for the oxygen, we have a total of 16 plus 9, that's 25. So here, I would put 25 over 2, and then I would simply multiply everything by 2 to get 2C8H18 liquid plus 25 O2 gas to give 16 CO2 gas plus 18 H2O liquid. All right? Okay, then we need to figure out, basically, based on this equation, the amount of heat change occurring for 2 moles of octane. So I'm going to start off with, down here, 2 moles of C8H18, and I would convert that to grams. So down here, you're going to have 1 mole of C8H18, and up here, I would put the molar mass. So I'm going to do a bit of cheating here. I'm going to go to my molar mass calculator. And enter the formula C8H18 And according to my calculator, it's going to be a molar mass of 114.23. So here, up here, I'm going to put 114. Wait, what did I say? I'm sorry. Let me go back to 114.23. So 0.23 grams of C8H18. All right. And then the next conversion factor would put, I would put the value that is given in the question of the amount of heat released per gram of the substance. According to the question, that's 47.9 kilojoules per gram of octane.